Welcome to G Fun Facts Online. Today we are stripping away the gold medals, the national anthems, and the fanfare to look at the invisible machinery running the Winter Olympics. If you were to mute the cheering crowds and the announcer's voice, you would hear the true soundtrack of the games. You would hear the rhythmic clack of steel on ice, the violent scratch of a toe pick biting into a frozen surface, and the deadly hiss of air rushing over a spandex-clad body. To the casual observer, skating is an aesthetic marvel. But to the physicist, it is a chaotic battlefield. It is a war against friction, a negotiation with gravity, and a desperate race against air resistance. Every world record set on the ice is a triumph of engineering and biomechanics as much as it is a feat of athleticism. From the molecular slush that allows a blade to glide, to the aerospace-grade aerodynamics of a racing suit, the story of Olympic skating is, at its heart, a story of physics. Let's begin with the most fundamental mystery of the sport, a question that seems simple but stumped scientists for over a century. Why is ice slippery? Before a skater can even think about a triple axel or a 500-meter sprint, they must contend with the surface beneath them. For a long time, physics textbooks offered a simple, elegant explanation called pressure melting. The idea was that the thin blade of a skate concentrates the skater's entire body weight onto a tiny surface area, creating immense pressure. This pressure, the theory went, lowered the melting point of the ice just enough to create a thin film of water, upon which the skater glided. It sounds plausible. It feels intuitive. But the math simply does not hold up. If you take a 160-pound skater on a standard blade, they generate a pressure of roughly 400 atmospheres. While that sounds substantial, in the world of thermodynamics, it is only enough to lower the melting point of ice by a fraction of a degree, perhaps to negative 3.5 degrees Celsius. Yet, we see skaters gliding effortlessly on ice that is negative 10 degrees or colder. If pressure melting were the only factor, skating on a bitter February morning in an outdoor rink would be like trying to slide across a concrete sidewalk. So what is actually happening? The truth lies in a combination of two more complex phenomena known as the quasi-liquid layer and friction melting. Ice is not a static solid. At the molecular level, the surface of an ice crystal is chaotic. While the water molecules deep inside the ice crystal are locked in a rigid hexagonal lattice, the molecules at the very surface are untethered. They vibrate and rotate, forming a disordered layer that behaves more like a liquid than a solid, even at temperatures well below freezing. This quasi-liquid layer is only a few molecules thick, but it provides a natural lubrication. However, that is just the start. When a skater pushes off, they engage the second engine of slipperiness, which is friction melting. As the steel blade drags across the ice, the friction generates heat. This is not the heat of a fire, but a microscopic flash of thermal energy that instantly melts the ice directly beneath the blade. This creates a thicker, temporary film of water, a hydrodynamic lubricant that reduces the coefficient of friction to near zero. This delicate thermal balance makes the job of the Olympic ice meister one of the most stressful in sports. Mark Messer, the legendary ice technician from the Calgary Olympic Oval, knows that the difference between a gold medal and a fall is often a fraction of a degree. This is why speed skating and figure skating require completely different surfaces. For long-track speed skating, the ice must be hard and fast. Technicians aim for a surface temperature of around -7 to -9 degrees Celsius. This hardness minimizes the friction coefficient, allowing the skate to glide with minimal resistance. However, it must be just soft enough to allow the sharp edge of the blade to bite during the push-off phase. If the ice is too hard, the blade will skid out under the immense lateral force of a sprinter's stride, causing a blowout. Figure skating, on the other hand, demands a completely different canvas. Figure skaters need soft ice, typically kept at -3 to -4 degrees Celsius. The warmer ice allows their deeply curved blades to carve intricate edges without skidding, and provides a softer landing surface for the massive impact forces of a quadruple jump. If a figure skater were to attempt a quad lutz on speed skating ice, the brittle surface would likely shatter under the toe pick impact, potentially causing a catastrophic injury. Now, let's shift our focus from the ice to the air. In speed skating, the enemy is the atmosphere itself. At elite speeds of 60 kilometers per hour, a human being is a terribly unaerodynamic shape. Over 80% of a speed skater's energy output is spent simply pushing air molecules out of the way. This is why the sport has become a hotbed of aerospace engineering. Before we even discuss the suits or the skates, we have to talk about the venue. The holy grail of speed skating records is altitude. The physics is simple. Air density decreases as you go higher. Less dense air means fewer molecules colliding with the skater, which means less drag. This is why the Olympic ovals in Calgary and Salt Lake City are known as Highland tracks. A skater performing the exact same physical exertion will finish a 1,000-meter race roughly 1 to 1.5 seconds faster in Salt Lake City than at a sea-level track like Sochi. In a sport decided by thousandths of a second, that is an eternity. But Mechanical engineering has played just as large a role as geography. The single greatest mechanical leap in skating history occurred in the mid-1990s with the introduction of the clapskate. For a century, skates were fixed. The blade was rigidly attached to the boot at both the heel and the toe. This design had a major biomechanical flaw. To push off, a skater extends their leg backward. With a fixed blade, as the leg extends, the heel of the skate must eventually lift off the ice. As soon as the heel lifts, the blade tip digs into the ice, cutting short the gliding phase of the push. The skater is forced to pick up their foot early to avoid tripping over the toe. Dutch biomechanist Gerrit Jan van Ingen Schenau saw this as wasted energy. He developed a skate where the blade was attached only at the toe by a hinge. The heel was free to lift. The physics of the clapskate changed everything. Now, as the skater extended their leg, the blade could remain flat on the ice, even as the heel lifted. This extended the push phase of the stride, effectively lengthening the skater's leg. It allowed the skater to continue applying force against the ice for a fraction of a second longer with every stroke. When the clapskate debuted at the 1998 Nagano Olympics, world records were obliterated. In the men's 500 meters, the record improved by over 2 seconds, a margin that previously would have taken a decade to achieve. While the skate manages friction with the ice, the suit manages friction with the air. When air flows over a moving object, it forms a boundary layer. If this layer flows smoothly, known as laminar flow, drag is low. But on a human body, with its curves, shoulders, and hips, the air tends to separate from the surface, creating a turbulent wake of low pressure behind the skater. This pressure drag pulls the skater backward. To combat this, engineers borrow a trick from golf balls. A smooth golf ball travels half the distance of a dimpled one. The dimples create a tiny layer of turbulence near the surface, which paradoxically helps the air stick to the ball longer, delaying separation and reducing the size of the drag-inducing wake. Speed skating suits are designed with this principle in mind, using textured fabrics and rubberized patches to trip the air into a turbulent boundary layer. However, aerodynamics is a fickle mistress. In 2014, the US team partnered with Lockheed Martin to create the Mach 39 suit. It was touted as the fastest suit ever made, featuring vents on the back to release heat. It was a disaster. Skaters complained that the vents allowed air to enter the suit, puffing it up like a parachute. The suit, designed in a static wind tunnel, failed to account for the dynamic shifting posture of a tired skater. It was a harsh lesson that theoretical aerodynamics must survive the chaotic reality of human movement. That chaos is nowhere more evident than in the corners. Watch a speed skater on the straightaway, and you see power. Watch them in the corner, and you see physics on the edge of catastrophe. The corners are where races are won or lost. Here, the skater is fighting centripetal force, the need to constantly accelerate toward the center of the circle to maintain a curved path. To do this, they lean at precarious angles, sometimes exceeding 50 degrees relative to the ice. The physics of the crossover step is brilliant. By crossing the outer leg over the inner leg, the skater can maintain continuous power generation while leaning. The incredible lean angle allows the skater to use the ice's reaction force to push them not just forward, but inward, countering the centrifugal pull that wants to throw them into the padding. Short track skaters take this to the extreme. Because their track is tighter, the centripetal forces are massive. They rely on their hand touching the ice to create a third point of contact, stabilizing their extreme lean. They are essentially falling into the turn, trusting their speed to keep them upright. Now, let's leave the racetrack and move to the figure skating rink, where the physics changes from minimizing friction to exploiting it. Figure skating is about generating vertical velocity and rotational momentum. The modern era of the sport is defined by the quad revolution, the race to add more and more rotations to jumps. A figure skater entering a jump is a study in the conservation of angular momentum. The equation is L equals I times omega. L is angular momentum, or the total spinning energy. I is the moment of inertia, which represents how spread out the skater's mass is. And omega is the angular velocity, or how fast they spin. Angular momentum is conserved. This means that once the skater leaves the ice, their total spinning energy is fixed. They cannot generate more spin in the air. To spin faster, they must drastically reduce their moment of inertia. This is why skaters pull their arms and legs in so tightly. A skater with arms extended has a high moment of inertia. By snapping their arms to their chest and crossing their legs, they reduce their radius. To compensate, their rotation speed accelerates violently. A skater in a tight scratch spin can rotate at 6 revolutions per second, which is faster than a helicopter blade. The difference between a triple and a quadruple jump is a math problem that pushes human physiology to its breaking point. To complete a quad, a skater needs 2 things: time in the air and rotation speed. Time in the air is determined solely by vertical velocity at takeoff. Rotation speed is determined by torque at takeoff and body position in the air. The cruel irony of physics is that these 2 goals often conflict. To jump higher and get more hang time, you need more muscle mass in the legs. but more muscle mass increases your moment of inertia, making it harder to spin fast. This is why the quintuple jump, or 5 rotations, is considered the theoretical limit of the human body. The average elite skater stays in the air for about 0.6 to 0.7 seconds. To add a 5th rotation without spinning faster, a skater would need to jump roughly 50 inches off the ice. For context, NBA superstar LeBron James has a vertical leap of about 40 inches, and he isn't wearing heavy steel blades or moving on slippery ice. If we look at the quad axel, first successfully landed in competition by Ilya Malinin in 2022, we see the hardest jump in the world. Unlike other jumps where the skater takes off skating backward, the axel requires a forward takeoff. Because they are moving forward, they must complete an extra half rotation, making a quad axel actually 4.5 rotations. The physics of the axel launch involves transferring linear momentum into vertical and rotational momentum, using nothing but the friction of a single metal edge. The skater must break their forward motion instantly by turning the blade sideways and vaulting over the toe pick. It is a violent conversion of energy, and what goes up must come down. The landing of a quad jump subjects the skater's body to impact forces of 5 to 8 times their body weight. For a 150-pound skater, that is over 1,000 pounds of force slamming into a single ankle on a blade just 4 millimeters thick. This repetitive trauma is why stress fractures are the plague of figure skating. As we look toward future Olympic Games, physics continues to drive the sport. The line between equipment and cheating is blurring. In speed skating, haptic suits which vibrate to tell a skater if their posture is too high are already used in training. New blade materials, like carbon fiber runners with diamond-polished steel edges, are reducing friction even further. In figure skating, AI is being used to analyze jump physics in real time, tracking the skater's center of mass and rotation speed to optimize takeoff angles to the single degree. Breaking the 1-minute 40-second barrier in the 1,500 meters or landing a quintuple jump will likely require a perfect storm of atmospheric conditions, advanced materials, and perhaps a genetic anomaly of an athlete. When you watch the Winter Olympics, you are watching a grand experiment. You are seeing how far the human body can be pushed when aided by the laws of physics. The speed skater crouched at the starting line is a projectile waiting to be fired, wrapped in a suit designed by aerospace engineers, balancing on blades that melt the ice beneath them. The figure skater spinning in a blur is a living gyroscope, fighting to conserve momentum while defying the crushing gravity of the landing. They are not just athletes. They are physicists in motion, writing equations on the ice with steel and sweat, forever chasing the elusive limit of frictionless speed. Thanks for listening to G Fun Facts Online.